Hello, my name is Vladislav, and I am an engineer at VTM Group. Today, I will present to you the hard-bearing balancing machine 9D718. The main parts of the machine sit on the base. You need to secure the base to the concrete floor with anchor holes on one side and on the other side of the bed. On the bed there are support number 1, support number 2, and belt drive. Support number 1 consists of the main bearing part of the support, a roller block, cassettes on 2 rollers, prisms, and an axial support. Movement of the support on the bed is realized by means of a chain drive transmission, which is located in the central part of the bed. In order to move the support, it is necessary to unscrew the fixing bolts on all 4 sides and then use a 24 wrench to move the support along the bed. Again, these 4 bolts located on the edge of the bed are used to secure the bed supports. Support number 2 has an absolutely identical construction. The belt drive also consists of 3 rollers and a drive pulley located on the electric motor. One of the rollers functions as a tension roller, which is operated using a screw mechanism with trapezoidal threading. When the handwheel moves, the roller moves either closer to the center of the bed or further away from the center, thus tensioning of the belt. The 2 central rollers have a scale on the top to make it easier for the operator to orient themselves according to the rotor diameter so that the belt drive slings can be slid, to have the belt drive straps go straight up and down. The rollers are moved by releasing the screw on this side and moving the roller along the groove. Similarly, on the rear side, the rotor is installed either on rollers or on the prisms, which are located in this case on the side. The prism can be inverted and the rotor placed on the prism. Maximum recommended weight when balancing on the prisms is up to 50 kilograms. A protective bracket is located at the top of the support, which is fixed to the support when it is in a closed position. This bracket is also necessary for positioning and balancing parts on the machine that will be cantilevered relative to the supports. The axial stops are located at the ends of the body of the measuring bearings. They are able to shift the vertical section in relation to the horizontal and another vertical strip for the construction under the rotor's axis center. Additionally, there is a bearing on the upper side of the folding bracket for support against the rotor journal when necessary. Machine control panel. The main stand consists of a computer with a measuring system, control buttons, and a main switch located on the side. On the control button, there is a rotor rotation stop button, rotor rotation start, potentiometer with rotor rotation speed selection, indication lamp, which signals that the rotor is rotating at the set speed. Changing the direction of rotation forward or backward, clockwise or counterclockwise. Acceleration and deceleration time, and also manual and automatic operation. The following action will be required when removing and installing the rotor. Release the locking bar, swing out the hinged bracket on one side and on the other. Pull aside the speed sensor. Loosen the belt drive. Move the belt to the side. and then use a crane girder to lift the rotor and move it away from the machine. Installing the rotor means placing the rotor by crane beam on the surface of either rollers or prisms. The machine provides height adjustment of the cassette, so we can install the rotor with different journal diameters. Adjustment is carried out by unscrewing two nuts and turning the center nut on the axle. This will ensure either raising or lowering of the roller block. After the rotor has achieved the required horizontal alignment, the nuts must be clamped. The axial stops are then brought in. The axial stops are brought in such a way that on one side we have a ball in the center of the rotor, and the axial stop rests on that ball, and the height is the same. On one side, we make contact between the ball and the bearing. On the other side, we have clearance. There should be a guaranteed clearance here. Once we've got the rotor in place and we've got the axial stops in place, we can safely rotate the rotor either on the machine rollers or on the prisms. The next step is to put the belt on. We execute it as shown in the illustration. We wear the roller skates and fix them up, and tighten the belt. Once tightened, we rotate our hand a few times to ensure that the belt is fully centered. If we see that the belt starts to stick to any of the rollers when turning it by hand, we should repeat the procedure again. The belt tension should be sufficient to prevent the belt from slipping during rotor pulling, acceleration, and braking. If the tension is insufficient, it should be increased. We close them after the rotor is installed and lock them in place. Next, we will configure the laser marker. It has a ray. We direct the ray to the surface of the rotor. A contrast mark will be pre-marked on the rotor. We place the mark vertically on top of the rotor, and we position the laser so that it shines on our mark. There are two adjustments on the laser housing. Right now, our sensitivity is a bit insufficient, and we are interested in adjusting the sensitivity. We increase it so that the indicator light comes on when the laser beam is on the mark. And when we're turning the rotor, it won't light up and will blink once when the rotor passes the mark. So we need to get the optimum sensitivity so that there are no false positives. And at the same moment, there's a true trigger when the mark passes. The second indicator allows you to set a dark or light mark. Now we have a light marker set. The potentiometer is turned to light. Then we close the second protective bracket. If necessary, we can lower the vertical stops and bring the bearing closer to the rotor journal. This is not necessary at the moment. The next step is to adjust the measuring system to the specific rotor. To do this, we need to start the machine with the switch on the side. After that, we will have the software running and automatically start the program. To adjust the machine for a certain rotor, we must enter the modes menu and select the calculation mode. In calculation mode, there are three options for calculating the balancing tolerance depending on the input data. We are now going to look at setting to the smallest specific imbalance we can achieve. We set it to roughly 10 microns. The mode can also be selected depending on the rotor type. To determine the rotor type, we press Help, and using the accuracy classes, we will select the rotor that matches a class. Usually it is the 3rd, 4th, 5th class of accuracy. Setting the rotor's maximum speed, we enter the radii of the rotor, radii of the correction planes. If the rotor is between the machine supports, and its center of mass is at an equal distance from the surfaces of the necks, then these two values, they must be equal but above 0. Next, the rotor mass is entered. When we need to enter the mass, we simply click on the desired box and enter the value. We press Enter to confirm the selection. After entering all parameters, we press Calculate. By class 100, that's a lot. Let's class 6, 6.3. This is more than it seems to be true. According to accuracy class G, 2.5. Now the balancing tolerance will be 5.2 grams. Pressing Enter, confirming the selection. Moving forward, we will have to implement the existing test load that should fall within the range of 5 to 20 tolerances. For each plane, the tolerance for a particular plane is 5.2 grams. Accordingly, we multiply it by 5, multiply it by 20, and any weight that falls within this range can be used as a test mass. The weight of the test mass is entered in the lower field. I have the weights already prepared. I will use a bolt. The mass of the bolt is 16.25 hundredths of a gram. Enter it here. And press Enter. Next, select Start without test weights. Set the rotation speed to minimum. Press Start Rotation. Spray a little oil. Lubricate the rolling surface on one side and on the other. Increase the rotational speed. Press Start Measuring, and we will observe the speed here. The minimum speed at which is 200 revolutions per minute. We increase the speed smoothly. In the range of 500 revolutions. We wait for the stop button to become active. In this case, it is already active. Then, we look at how stable the angles and sizes appear for each plane. If the angle changes by more than plus or minus 5 degrees, it will be necessary to enable averaging. This is not necessary now. We press Stop Measurement and Stop Rotation. The launch without test weights is done. Next, run with the control weight in the 10-degree plane. Here's my weight in plane 1625. I'm placing it on the first correction plane on the left side. 0 degrees is where the mark is located. I screw this bolt in. All the way in. Next is the start I have already selected. I press the start button to rotate. I wait for the green light to turn green. Lights up. And I press the start measurement button. Then I wait for the stop measurement button to become active. It became active, and since then, I have been monitoring the stability of how the angles of the quantities are displayed. Everything is stable. I press the button, stop measurement, stop rotation. I select the start with the load 1625 on the plane 2 by 0 degrees. I've got the launch selected. I wait for the rotor to come to a complete stop. I turn the rotor so I can work with it comfortably. I unscrew the test weight from the first plane and move it to the second plane. Do the same against the mark. I press the start rotation button. I wait for the indication that the rotor has accelerated to the set speed. The rotor has accelerated. Press start measurement. Waiting for the stop measurement button to activate. The stop button for measurements is active. We are watching the stability of the angles and values shown. Everything is stable. Press stop measurement, stop rotation. Next, we observe the values in the table. We see that during the 0 start, the vibration was relatively low. During the weight installation on the first plane, the vibration level increased, and the signal on the second plane also increased slightly. When the weight was placed on the second plane, the signal increased more on the second plane. On the first plane, the signal also increased, but not so much. Then I press the result button. I save the rotor under some name, which will be displayed in the balancing report later on. To change the name of the rotor, click on the name of training field and type in whatever we want. Press enter to confirm, and press save. After that, we will have to remove our control weight. Start the rotation. The rotor has accelerated. The automatic unbalance measurement process has started. Wait for the stop button to become active. The stop button is active. The angles are stable. Press stop measurement. We move to the previous measurement and compare the results. We see that there is a small difference, but it's within much smaller than the balancing tolerance. We have no correction on the right side. It's within tolerance. The left side needs correction. The tolerance is 5.2. The actual imbalance is 557. In order to make the correction, we select the imbalance correction method, addition. And we weigh 5 grams. 436, just a little bit more, 507, that'll do it. Weigh 5 grams and rotate the rotor until the orange sticker on the edge of the circle aligns with the vector. Rotate the rotor and look at the screen. The orange sticker has matched the vector of the imbalance location. This means that the unbalanced location is vertically on top of the first plane, in the position where the sensor is shining. In that plane, after we have positioned the weight, we move back to the control panel and activate the start button to commence operations. We wait for the indicator to light up, signaling that the speed has been reached and the measurement will begin. The rotor has accelerated. The measurement has started. Next, we wait for the stop button to become active. stop button is active. We watch the stability of how angles are shown. Everything is stable. The angle does not change. The magnitude also does not change. We press stop to stop the measurement. In the last launch, I had a left side imbalance of 5.57, and after correcting it, I had 259 milligrams remaining. On the right side, there is a slight variation in both angle and magnitude, but it is well within tolerance, so no additional corrections are needed here. Once the rotor has been balanced, we proceed to press the report button. Create. We enter the last name of the operator. We select the first run as the initial unbalance, the last run as the final unbalance, and we press the button Create. This generates a protocol. It includes the name of the rotor, the speed at which it was balanced, the radius of correction on the first and second plane, initial imbalance, permissible imbalance, and final imbalance. It's 676 grams per millimeter, called the permissible imbalance. 730 grams per millimeter represents the initial imbalance. And final imbalance is represented as 33 and 6 on the first plane and 94 and 5 on the second plane. Next, in order to save the count, we click on the floppy disk. Enter a number, or the name under which this report will be saved, and press Enter. The report is saved. You could also select the folder where the report will be located. To exit, press the cross. Press Out, and go back to the balancing mode. The main balancing screen features the following buttons for your convenience. When you press the Plane 1 button, we enter a menu that allows us to transfer the correction plane from one to another. The diagrams are located in the pictures. We enter the distance in millimeters by which we will transfer the correction plane. We press Calculate, and we will have Plane 1 written in italics, and we will see the actual value of unbalance in another recalculated plane. To exit this mode, click here. Tap Cancel. Plane 1 and Plane 2 are written in standard font for us. There's also a button called Static Moment Balancing. This is the division of types of imbalance into static and dynamic components, or static and moment component. Here you can also see the previous results, the next results. We cannot eliminate the torque here. We can eliminate only the static component in this menu, which will be highlighted separately. Press Close. The next sub-item is Averaging. It is switched off at the moment. It can also be switched on if necessary during rotor rotation and unbalance measurement. The next menu item is Eccentricity Accounting of the tooling. It only works at the time of the last measurement. The next submenu is Counting Direction. It can be either forward or reverse. The operator chooses the counting direction that is convenient for him. The next button is Unbalance Correction Method. It can be either add or remove. The next one is Radius of Correction. On the first and second plane, it is individually selectable, as is the Method of Elimination. The next button is Units of Imbalance Measurement. It can be measured in grams, grams per millimeter, or microns, depending on the setting. If we were to select a setting where we would only enter the tolerance in grams per millimeter, we'd have a choice of grams per millimeter or grams. The next button is the Modes button. We have Calculation Mode, Settings, Balancing, Memory, and Close. Functions. Several functions are provided for the convenient balancing of various specific rotors. Their operation can be found in the instructions supplied with the machine. Report button, previous measurement button, start rotation, and exit button are the options. On the remote's left side, the switch displays the pictograms for manual and automatic, indicating that the machine is operating in balancing mode. If manual mode is in effect, the operator starts rotor rotation and stops it. If automatic mode of operation is selected, then the operator presses the Start Rotation button of the machine, after which the rotor is accelerated to a fixed speed. Unbalanced measurement starts. After the unbalanced measurement, the machine automatically shuts off the measurement and rotation. Since we had the static moment balancing function enabled, we switched to this mode. To turn it off, press the off button. The machine's base is installed on the workshop floor, which is made of a concrete foundation at least 200 to 250 millimeters thick. It is fixed with anchor bolts through the appropriate holes in the bed. If there is a gap between the bed and the base, metal pads can be used to compensate for this gap. The machine connects to a three-phase system of 380 volts, including 3 phases and a ground wire, as well as a neutral wire. The grounding of the machine is connected to the side panel of the electrical cabinet. The bed grounding is located on the back of the bed. The machine is connected as follows. The grounding wire is first connected to the side of the control cabinet and to the bed. Next, open the cabinet and connect the power supply wires from the left side to the terminal block, starting also with the ground cable. And on the right side, the electric motor is connected. The electric motor is connected according to the phase markings. Do not mix them up. The power part of the connection is finished. Now we move on to the signal part of the connection. There are 2 doors at the back of the control cabinet. We open one and the other. Here is the measuring device, which is connected to the cables from the machine, from sensors, speed sensors, and rotor position sensors. They're secured by means of strips placed around the edges. Cables enter through the cable gland at the bottom and are connected according to the markings into the unit. After that, the doors are also closed. The machine can now be switched on.